How's everyone doing today? Y'all ready? Questions? Any questions? Which one? 46. "46" was a bit much, wasn't it? Man, you're reading my mind over there. Okay, I've been asked about this problem number 46. It's going to take a while. All right? So please pay attention. There's a lot involved in this problem. You're trying to find the maximum, minimum values of hopefully a continuous function on a closed interval. So let me first talk domain of the function to make sure that I have a continuous function on the interval that's defined here. So t just by itself, that's continuous everywhere, right? That's just a polynomial, plus cotangent. So let me investigate cotangent of 1/2 t. Cotangent is cosine, right? 1/2 t over sine 1/2 t. That's what that is. I just want to make sure that this is defined everywhere. But there are some situations when sine is 0, right? So let me see here. When would this possibly be 0? When does sine of 1/2 t equal 0? So then you go to your unit circle and you say, when is the sine function 0? At what angles? 0 and pi, right? That means you need the argument of this trig function, 1/2 t, to be equal to 0 or pi, or 2 pi, or 3 pi, or 4 pi. So I need all the general solutions here. What's this general solution of these 2 points? 0 plus pi k, or pi n, right? We did that last class. So I could just say pi n. So the argument, that's the angle in here, has to be equal to some multiple of pi. I multiply both sides by 2, and I get 2 pi n. So that means if t is any multiple of 2 pi, this function is undefined, isn't it? This is undefined if t is a multiple of 2 pi. So I look at my interval. My interval is between pi over 4 and 7 pi over 4. So if I go to my unit circle, pi over 4 is here, isn't it? 7 pi over 4 is here. I'm looking only in this interval. In that interval, do I ever hit a multiple of 2 pi? No, I do not. Do you all understand that? So do I have any domain issues? No. Therefore, this is a continuous function on this closed interval. What if this interval was 0 to 7 pi over 4? Then I'd have a problem. And then the closed interval method wouldn't work. So I do have a continuous function on closed interval AB. I had to check that to start, all right? So I'll need to now find the critical numbers. So I'll need to take a derivative. The derivative of f with respect to t is 1 plus, well, is it plus? What's the derivative of cotangent of something? Negative cosecant squared of that something. So this is going to become negative cosecant squared of that something. Am I done? Then times the derivative of what was inside. So chain rule. Derivative of what's inside is what? 1/2. So my derivative is 1 minus 1/2 cosecant squared of 1/2 t. All right, that's my derivative. What am I going to do with this derivative? Set it to 0 and figure out where it's undefined, right? So let's start with setting it equal to 0. If I set the derivative equal to 0, I'm setting 1 minus 1/2 cosecant squared of 1/2 t equal to 0. My fan turned out to be a disappointment. Yeah. Yeah. It just, I mean, it was spinning. It sounded like it was moving a lot of air. It just didn't do it. So I got rid of that. So I got smaller ones. I got like 2 smaller ones that are like high velocity outdoor fans, and they work great. So problem solved, but it was just a headache to have to install and uninstall 2 ceiling fans and be all excited. All right, let's solve this. This is a trig equation from pre-cal. I'm trying to figure out what t is, which makes this true, right? So I'm going to first move, let's just move this whole negative thing to the other side to make it a positive. Let's also now multiply both sides by 2. Trying to isolate the trig function. Let's get rid of the squared by taking the square root on both sides. When I take the square root of the left side, I have to do plus or minus. You all right with this? Any questions? And now I have to figure out when is cosecant of something equal to positive or negative root 2. This might be difficult for you to remember. Cosecant is 1 over sine, isn't it? And if you multiply both sides by sine of 1/2 t, you would get this. And if you divide both sides by positive and negative root 2, you get this. And if you rationalize the denominator on the right side, what do I mean by rationalize the denominator? Multiply top and bottom by root 2, you get root 2 over 2. Now the reason I did all that was to help us see that we're really saying where, at what angle do we get the y coordinate on the unit circle to be root 2 over 2? And that's one of the common angles, isn't it? Common values? Yeah, so let me draw a unit circle. Where's the y coordinate positive or negative root 2 over 2? It happens here, or here, or here, or here, right? Any of those 4 corners, your y value, because you're looking at sine, your y value is root 2 over 2? root 2 over 2, or negative root 2 over 2. We okay with this? So I want to know when my argument, the angle that I'm plugging into the sine function, is equal to one of those angles. But give me those angles in general. What's the general representation of these angles? So what is this angle? What's that angle? Pi over 4. How much do I have to rotate by to get to this one? 90 degrees or pi, right? And then how do I get to the next one? Another 90 or another pi? Not pi, pi over 2. Sorry. Or another 90 to go pi over 2 again. Or another pi over 2. Or another pi over 2. So couldn't I start at pi over 4 and then just add multiples of pi over 2? And that would take you around? Y'all see that? Show your hands. How many of you remember getting general solutions to trig equations in pre-cal? General solutions. Okay. So, I mean, this would be one of those things where if you get to a test and you still have not resolved this, you can't expect to do well, right? So you need to make sure you address that. Tutoring, getting help, something, right? It's a prerequisite topic. So pi over 4, I need pi over 4 plus pi over 2, n. That's what my argument has to be equal to. So I need my 1/2 t to be equal to pi over 4 plus pi over 2 n. So pi over 4 starts you out. Pi over 2 n gives you the quarter rotations. Quarter rotation. And now solve for t. So multiply both sides by 2. T equals 1/2 pi plus what? Pi n. Y'all okay? All right. No one's answering me. I shouldn't be surprised. No? Y'all don't usually respond, right? You don't usually say anything. Okay. All right, now this is it. This is where I'm going to have critical numbers. But I can only be looking in the interval that we have here. The interval we have is what? Pi over 4 to 7 pi over 4? So do any of these lie in that interval? So let's start with n equals 0. If n is 0, what's t? Pi over 2? Half pi? Does that live in our interval? Yes. Okay, how about n is 1? If n is 1, you have pi over 2 plus pi, which is 3 pi over 2. Does that live in the interval? Yes. Do you know what interval I'm talking about? This one right here, which we said was here. Okay, pi over 2 lived in there, and then 3 pi over 2 lives in here. I don't think anything else is going to live in here, though. Do you agree? If we let n be 2, you get t equals pi, half pi plus 2 pi, which is 5 pi over 2. 5 pi over 2 is outside of 7 pi over 4. Or wait, was it 7 pi over 4? Yeah. So that's outside of that, so I can stop. There are 3 critical numbers. 3? No, 2. 2 critical numbers. Here they are. Pi over 2, 3 pi over 2. All right. Are we done finding critical numbers? No? What else do I have to do? I have to look at where the derivative does not exist. That's what I'm going to look at now. So I forgot what my derivative was. Here it is. Oh, wow, just copy it again. And bring it over. Get rid of the equals 0 because that's not what I want. I just want to know when this thing is undefined. Cosecant, right? Cosecant is 1 over sine. So this is going to be undefined when sine of 1/2 t is undefined. I already did that, didn't I? When I was looking at cotangent, right? cotangent, I was looking at denominator sign. I was saying when was that 0? And we already know that didn't happen in our interval, did it? So we don't have to do any work for this because we already know that it cannot be, sine cannot be 0 in the interval we're looking. So not a problem in the interval pi over 4, 7 pi over 4. So we're good here. So I've got my critical numbers. Now I take those critical numbers, I plug them into the original function, right? I take the endpoints, plug them into the original function, compare all the answers. So I want to evaluate my original function at the critical numbers, which were what, pi over 2, and at 3 pi over 2, and then at the endpoints, which are pi over 4 and 7 pi over 4. The original function was t, which for us is pi over 2, plus cotangent of 1/2 t, which for me is pi over 2. Right? That's what the original function was. T plus cotangent of 1/2 t. I'm replacing t with pi over 2. So that gives me pi over 2 plus cotangent of pi over 4. What is cotangent of pi over 4? It's cosine of pi over 4 divided by sine of pi over 4, right? It's 1. Prerequisite material is what this is, right? Cotangent of pi over 4 is cosine of pi over 4. What's cosine of pi over 4? Root 2 over 2. What's sine of pi over 4? Root 2 over 2. What's root 2 over 2 over root 2 over 2? It's 1. Tangent would be 1 also. Cotangent is the reciprocal, so you could do it that way. So that's 1. I don't say prerequisite material to be an ass. I'm saying it because that's why it is required for a course like this, because we don't have time to go through and me show you how to find general solutions. I mean, I'm answering a question to the homework, so this is an exception. But can you imagine if in every math class you had to go back all the way, like we get to a quadratic and I had to go back all the way to show you how to factor again? Or, I mean, you could never progress, could you? So that's why the subjects build upon themselves so fast. Next one. 3 pi over 2 goes in first for t, plus, now what's cotangent of what's going to happen when I plug 3 pi over 2 in there? 3 pi over 4? So where's 3 pi over 4? Second quadrant over there. You're taking cotangent, which is the x-coordinate divided by the y-coordinate. What's the x-coordinate? It'll be -1. -1 this time. So it'll be equals, over here, 3 pi over 2 minus 1. I'm sorry? I did put a cosine. Cotangent. Next one. Pi over 4 plus cotangent, did it again. Cotangent of what? Pi over 8. Now that's not a value that is on our unit circle that we know very well, is it? So this may be a point where you break out your calculator and you make sure you're in radian mode and you do cotangent or just do tangent of pi over 8, and then do 1 divided by that answer, or the reciprocal. And then same thing on this one. The cotangent is 2.4? Okay, and then add pi over 4 to that. Approximately 3.199. Okay, can you please do cotangent of 7 pi over 8? And then try and add 7 pi over 4 to that. It was negative, okay. And let's figure out what these are. Pi over 2 plus 1, and then 3 pi over 2 minus 1. And let's do those on a calculator, just see which is the biggest and smallest. 2.57, and then so it's looking like this is our max, and this is our min. Yes. It's not what... Are you in radian mode? What number was this? Okay, so if you plug in pi over 2, you get about 2.57, yes? If you plug in 3 pi over 2, you get 3.71. Is that what you had? Yes? If you plug in 7 pi over 4, you get about 3.08. Did I miss any of them? Pi over 4, 3.2. Is that what we have? So run through those again. Plug in pi over 4, you get 3.2. Plug in pi over 2, you get 2.57. Good. Plug in 3 pi over 2, you get 3.71. And plug in 7 pi over 4, you get 3.08. Yes? So that is correct. So you have a maximum when you plug in 3 pi over 2. The value is approximately 3.71. The exact value is 3 pi over 2 minus 1. So how did I say I like these answers? As points, right? So the first, your max is going to be at 3 pi over 2. And then if you do the exact form, 3 pi over 2 minus 1 is the y value. The minimum would be happening where? Pi over 2. And the value is pi over 2 plus 1. There's a lot going on there. Fantastic. Okay, anything else? I don't think I'm willing to go through an entire new problem, but do you want to look at 50 or 48? So, oh, you did those. Oh, okay. 49 was okay? Oh, I didn't get 49? Okay. All right, well, we will move on. We have an exam ever? Are we having an exam again? Let's see when our next exam is. April 28th. Oh, we still have a long way to go. Okay. So today we're going to start 4.2. What was 4.1 about? What was it? Closed interval method, right? So 4.1 was all about trying to find the highest and lowest points on a graph, right? Highest and lowest points on a closed interval. This section has very little to do with that. All right, so we're stepping away from that concept for just a minute. We're going to talk about what's called the mean value theorem. This is MVT. You've heard of theorems, right? Like a theorem? Theorem is a mathematical proof. It's an accepted fact, all right? This is a very, very pissed off theorem, right? That's what this means? Mean. This is mean. No, it's the average. Mean meaning the average. The average value theorem. So let's talk about where this comes from. The mean value theorem actually comes from a theorem called Rolle's theorem. So Rolle's theorem we start with, and then from Rolle's we'll get the mean value theorem. So I'll talk about it and then I'll come back to this visual. It's a pretty simple concept, Rolle's theorem. Rolle's theorem says this. Let's say that you have a function that starts, I'll start it at A, and it ends at B, and that they're the same, that at the beginning and at the end, the value of the function is 0. So f of A equals f of B equals 0. Now, not a whole lot of functions are going to start and end at the same place and it be 0, but just stick with me on this. If this is a continuous function, continuous meaning I try and connect these 2 points together and I can't pick up my pencil, then if I do that, there must be somewhere inside this interval, somewhere, where if I look at this point called C, and I look at the slope of the tangent line, the slope of the tangent line here is what? 0. It's flat, right? It's flat. So look at the slope of the line connecting the 2 endpoints. What's the slope of this line connecting the 2 endpoints? 0, right? Somewhere in between A and B, my derivative is also 0. Is there any way to draw this where that wouldn't happen? A corner. Good. So what if I try and draw this? Here comes my function. Right? Okay. So what's the slope of the line connecting these 2 points? 0. Is there a point in between here where the slope is 0, the derivative? No, right? Rolle's theorem says there has to be. But see, being continuous is not enough. What other condition must you have? Differentiable. See, what's happening at this corner? You can't have a derivative at a corner. So what if I tell you not only does the function connect these 2 points together, you can't pick up your pencil, but you can't have a corner, or cusp, or a jump. Well, jump would make it discontinuous anyway, but then is there any way to do it without having that slope be 0 somewhere? Rolle's theorem says you have to have that happen. Somewhere the derivative has to be 0. So let's look at the theorem. Let f be a function such that it's continuous on the entire interval. Draw it without picking up your pencil. It is differentiable on the inside, meaning there's no corners or cusps. The endpoints, f of A and f of B, are equal. Then there must exist a number inside the interval, in there, somewhere in there, such that the derivative at that point is 0, which is the same as f of B minus f of A. So here's Rolle's theorem. So there's a continuous function, and it's differentiable, right? No corners or cusps. Then there is a point right there in the middle. You can see it. The slope of this tangent line is parallel to this line, isn't it? In other words, they both have the same slope, which is 0. Here's another example. Is that a continuous function? Is it differentiable? Yes. So I'm guaranteed that there exists a number inside somewhere where the derivative is 0. Do you all see where it is? Can you already see it? There's actually 2 places, right? Rolle's theorem guarantees the existence of at least 1. It is possible to have 2 or 3 or 4, but you must have 1. Understand? How about this one? Is that a continuous function? Is it differentiable? Yes? So where is it going to, where in there is the slope of tangent line going to be equal to 0? At every point. Every point. So the first example, Rolle's theorem gave us 1 point in there. Second example had 2, and this is actually infinitely many points. But the theorem guarantees us 1. Understand or not? Visually understand what's happening? Okay. From the Rolle's theorem, we get the mean value theorem. So I'll go through it, and then I'll explain what this last piece means. Let f be a function that's continuous on a closed interval. Same thing as Rolle's, right? Let it be differentiable on the inside, so no corners, no cusps. There exists a number somewhere in there such that the derivative is equal to, and this is where the change is, all right? This is where things get different. Instead of the derivative being equal to 0, the derivative must be equal to this. F of b minus f of a over b minus a. What the heck is f of b minus f of a over b minus a? F of b minus f of a over b minus a. It's where the difference quotient came from. Let me show you. Let's say I have a here and b here. This time, my function does not have to have the same value. Okay, they don't have to have the same value. Rolle's theorem said they were the same, right, at the 2 points at the end. Let's say they're not the same. If I construct a right triangle, and I want to know the slope of this line, this height is f of b minus f of a, right? That's the change in y. Your change in x is b minus a, isn't it? Rise over run would be this over this. That's f of b minus f of a over b minus a. So the slope of the line connecting the 2 endpoints, right, is f of b minus f of a over b minus a. Understand? This slope right here, this slope is equal to f of b minus f of a over b minus a. So this new theorem is saying that if you're a continuous function on a closed interval and it's differentiable inside, no corners, no cusps, then somewhere inside the interval, there must be a place where the slope of the tangent line, f prime of c, is equal to the slope of the line connecting the 2 points. So here's the example. See that? That's Rolle's theorem, though, isn't it? That's just Rolle's theorem? Because these are the same value, aren't they? Okay, all that the mean value theorem is this. It's just turning your head. That's all it is. Right? All I did was turn my head. Look, these 2 values are not the same now, right? But if I'm going to connect from here to here with the smooth curve with no corners, the slope of this line, I have to have somewhere in here where the slope of my tangent line is parallel to this, right? Slope of tangent line is derivative. Slope of line connecting is this. Somewhere in there, they've got to be the same. Understand what mean value theorem says? Now, when you look at the line that connects 2 points, endpoints of a curve together, we call this the average value, the average. Okay, that's the average. The best way, I think, to look at it is if you look at it in terms of like distance and time. If you have time here, you have distance. Let's say you start at 0. Let's say 1, 2, let's say this is 3 hours. Let's say this is 60 miles. If I tell you started out at 0, drove somewhere, and at the end of 3 hours you were 60 miles away, what was your average speed? 20 miles per hour, right? You've gone 60 miles in 3 hours. The way you could compute that is by connecting these two together and drawing a triangle and finding the slope of that line. What's the slope of this line? Rise, which is 60, divided by run, which is 3, which is 20, right? The slope of that line gives you your average speed, doesn't it? The mean value theorem is saying this, that if you did this trip, now your graph wouldn't look like a straight line because you slowed down, you stopped at some stop signs, whatever it was. You got there eventually, right? The mean value theorem says that if your average speed over the whole trip was 20 miles per hour, somewhere in your trip, you had to go 20 miles an hour. At some instant in time, you had to be traveling that speed. It's impossible to have an average speed of 20 miles per hour and not go 20 miles per hour at some point in time. That's what the mean value theorem is saying. Do you all understand that? So, looks like in this picture, there would probably be multiple places, maybe like somewhere around here, like C1 we could call that, and then maybe, I don't know, somewhere in here. Looks like we would have another tangent line that's parallel to that this dotted one. And then maybe even a third one up here, right? Like this. Maybe there were 3 different places where I was going 20 miles an hour in this particular case. All right? Questions visually on what's happening? I'm sorry? Well, if you're not convinced that that would happen, Rolle's theorem is usually very convincing because you start and end at the same point. If I've got to connect these, I've got to go up, I've got to come back down. Eventually, my derivative is 0 there, right? This, you might argue that it couldn't happen. But I'll give you an example of one that might be a little more difficult for you to, not difficult, but a little more questionable. How about this right here, a function that does this? I don't know. Maybe you have an idea. I think even there that would be hard to argue. I mean, at some point you've got to be parallel to that line, right? Somewhere on there the derivative is parallel. Okay, so let's just see how the mean value theorem is going to work, like what you're going to be asked about the mean value theorem. So here's an example. Oh, let me write the mean value theorem down. Mean value theorem says if f continuous on the closed interval AB, f differentiable on the open interval AB, that means that your function has to be continuous on the closed interval. So at the endpoints, it has to be continuous. You only have to be differentiable on the inside. So it's okay if the derivative doesn't exist at the endpoints. What else does the theorem say? You have it's continuous, it's differentiable. Then there exists a C in the open interval AB. And this is a critical part of this theorem. The C, right? The place where this thing's happening, where the slope of tangent lines is parallel, is never at the endpoints. It's somewhere inside the interval. And then there exists a C somewhere inside such that the derivative of the function at C is equal to f of b minus f of a over b minus a. So we're saying the slope of the tangent line at C is equal to the slope of the what? What do we call that line that connects the two endpoints? When you have 2 points on a curve and you draw the line between them, we call that the secant line. When you move that point on top of the other one, we called it the tangent line. So secant line connecting endpoints. Okay, that's what the theorem says. The left side of this, that's the derivative. That's the slope of the tangent line at C. This is the slope of the secant line connecting the two endpoints. Mean value theorem says somewhere in there, they're the same. So here's the example. Verify the mean value theorem for f of x equals natural log x on 1e. So I'm going to bring up the graph of natural log x. I'm going to graph it on the interval 1e. I don't know what this is going to do with e. Okay. That did not like it. 1e. I'll do 2. The heck? 2.718. There. Okay, there's the graph of the function natural log x just on the interval 1e. All right? If I were to connect this endpoint down to this endpoint, then somewhere inside there, I should get a tangent line that runs parallel to that. Right? Somewhere. And I need to figure out where it happens. Understand what we're trying to do? So when they say verify the mean value theorem, they're saying find the C that makes it happen. Find where that is actually occurring. All right, so the way that we do this, when we're trying to verify mean value theorem, anytime you're asked to, is you're going to write down the mean value theorem, you're going to fill in the blanks, and you're going to work with the left side and right side down, left and right sides, and keep them equal the whole time, and that's how you'll solve your equation. But to do it, you're going to need the derivative, aren't you? So let's just find a derivative real quick. What's the derivative of f here? Derivative of natural log of x? 1 over x. Okay. Now the mean value theorem. Here's what it says. Mean value theorem says f prime of c must equal to f of b minus f of a over b minus a. All right. Let's check the conditions for the mean value theorem. I'll do it on the side. Is f continuous on this interval? Yes. Is f differentiable on this interval? Yes, because what's the derivative? 1 over x. The only thing that screws that up is 0, right? 0 will screw up the derivative, but 0 is not in our interval. So our function is differentiable. So that's it. This should work. So let's fill this table out. I'm going to work what I said, left side and right side down. What's the derivative at c? Well, 1 over c, isn't it? That's just your derivative at x is 1 over x, so derivative at c is 1 over c. Fill in the right side. Do you know what f of b is? What's the function evaluated at b? Well, what's b for us? The endpoint, which for us is e, isn't it? B is e, okay? And then what's a for us? A is 1. So I'm going to take e and plug it into the function, which is natural log. I'm going to take a and plug it into the function, which is natural log, and I'm going to divide it by b minus a. Into the function, not to the derivative, right? The original, yes. F of b, not f prime. So f of b would be natural log of e minus f of a, which would be natural log of 1 over e minus 1. E minus 1. Now this is an equation, right? The only thing that you don't know in this equation is c. Everything else is a number. So you just solve for c. What's the natural log of e? 1. What's the natural log of 1? 0. Over e minus 1, which is whatever that is. So I get 1 over c equals 1 over e minus 1. Which means c is e minus 1. You can just like cross multiply if you want. C is e minus 1. I've shown the existence of where it happens. That's the answer. Now, I'm going to go back up and take a look at this graph again. I would like to first draw a line. Nope. I want to draw a segment that starts out at 1, 0, and ends up at E1. Okay, see that blue line? Connects these. That's our secant line, right? We just said that if you go to E minus 1, which on your calculator, E minus 1 is about 1.718, something like that. If you go to about 1.718 and go up and look at the tangent line there, it should be parallel to that blue one. Now I'm going to have the computer do it for us. I'm going to have it grab, let me see, the tangent line at E minus 1. And I want a tangent. I think I'm there. I don't know. What do you think? Does that look right to you? Doesn't look right to me. It looks like there's a bigger gap down here than there is down here. Let me change this to 1, 7, 1, 8. That better? Yeah. Okay. Let me try E minus 1 again. Okay. You satisfied? Does it look like we have found the point in here where these are parallel? Yes? Okay. So every continuous function on a closed interval, which is also differentiable on the inside, must achieve its average value. Must achieve its average value. So there's an example that's not in your book, but I always tell my Cal 1 class about this because I think it's one of those good examples of how you could use calculus to answer a question that you may not really have resolution to otherwise. So here's my question. The car race, okay? Now, I'm not promoting car races, but let's just say that we have a race. We're looking down from the top. We're on a closed, restricted track, and these are professional drivers, right? It's my little disclaimer. Here's the start line. Here's the end, the finish. Car A is here, car B is here. Let's not even concern ourselves with how long the track is, but we start the race, they take off, right? They're racing, they're racing, they're racing. And then at the end of the race, it is, man. No, I haven't seen Fast 1, 2, 3, 4, 5, or 6 either, so I'm not feeling too bad about missing 7. I may have seen Fast 1. I'm not sure. At that time, I don't think it was called Fast 1. Yeah, I think it was. There was one that came out that's like Tokyo Drift or something like that. Which number was that? I think that was the one where I was like, all right, they're looking for ideas, I guess. I don't know. I haven't watched it. I don't know enough to criticize. Or if there's 7 of them, obviously people like them, right? Even Superman only had like 3. What, they haven't done it what? Okay, well, we're not going to get into this. We're going to get back to these 2 cars, okay? Because we're not going to debate Superman or Star Wars or correct chrono. You know what I'm saying. Forget. These cars start, they race, at the end, it's a tie. Dead tie, perfect tie. And this is theoretical, okay? It's purely theoretical. They start at the exact same time, they end at the exact same time. So here's the question. You ready for the question? Question 1. Was there ever a speed, or I should say, let me rephrase this. Is there a speed both cars had to go same speed? Okay, so that's the first question. So let me try and rephrase what this is saying. They raced, right? At every point in time, you look down at their speedometer and you've got, what their speed is at that instant in time, right? The question is there some speed, 40 miles per hour, that they both had to go that speed? The average one? Okay, so think about this. If they both started and at the same time, I'll let you, yes. Well, that's not what I'm asking, though. But I'm not asking that. I'm asking, is there a speed that they both shared? Is there some common speed that they both went at some point in time? Yes? Okay, so maybe we'll resolve it in a second. That's the first question. Did they ever go the same speed at exactly the same moment in time? Hold on. But not at the start or finish. Okay, so let's get our heads around these. The first one's easy, all right? Because it's very simple to explain what's happening. Okay, was there a speed that both cars went? Well, let's talk about their average speed. Do you agree that the distance both cars went are the same? Do you agree that the time it took them is exactly the same? So, because they tied. By the mean value theorem, they should both have achieved their average speed. Somewhere in their trip, they had to go their average speed. Do you agree? The average speed of both cars is the same. So at some point, they both had to be going their average speed, yes? Is problem number one settled? Yes or no? Okay, let's show hands since y'all don't like talking. Let's show your hands. How many of you are okay with question one is resolved? Yes? Okay. It's basically their average speed, right? Now, we would be assuming some things here. We'd be assuming it's a continuous, that their path is continuous. Or, and that it's differentiable. So what does that mean? Continuous differentiable. When you're looking at a car moving down a track, it doesn't all of a sudden disappear and reappear 5 feet later, right? It doesn't like vanish and jump. The speed doesn't go from positive to negative all of a sudden like that, like a corner, right? Everything is gradual. It's going to speed up, speed down through a smooth, continuous progression, yes? So we can assume that? All right. Number two, did they ever go the same speed at exactly the same moment in time? So think about this. You're traveling, you're racing each other, right? Was there ever a moment in time that you look at the speedometer in both cars and it's exactly the same speed at the exact same moment in time, not at the beginning of the race and not at the end of the race? Think about it. And then we'll vote. Okay? How many of you think that, yes, they did go the same speed at the same moment in time? Raise your hands. We're not going to hold this against you. Raise them higher. Yes. Okay. So how many of you think, no, it's not guaranteed? That's good. It's about 50-50. About 50-50. So those of you who think it is, explain. If you have a good rationale for it. I would agree. Do you all agree with that? That they pass each other? But who said that they passed each other? Yeah, but that's the thing. We don't need to watch the race. You're bringing up very good points. Because I agree. If I'm slowing down, speeding up, that at that moment in time, we look at our speedometers. Are they going to be the same? It sounds like a good argument, but I'm not quite sure I'm convinced that we have to pass each other. Right? What if this one takes off ahead, right? They start together, they take off ahead, and at the end, this one catches up and ties. It never overtakes them, but I said it can't be at the beginning and at the end. Okay? All I'm doing is I'm arguing with you because I want you to see the importance of this problem is that no matter what your argument is, I'm going to be able to argue against you. All right? So that's my argument against that. Yeah, see, that's harder for me to swallow. I'm not saying I disagree, but it's harder for me to accept that. Okay, for those of you who are against it and said that you don't think it'll happen, any good arguments for that? It may happen, maybe. It doesn't have to happen. Okay. All right, so you want to... So The reason I like this example so much is because this is an example of where you have a real life problem. Not necessarily that this would ever happen, but you have a real life scenario that you can argue. We've got half of the people in this class that basically think it's one thing and half that thinks it's the other, and we have no way of really proving who's right or wrong without mathematics. I mean, you cannot, we can sit here and let's arm wrestle, whatever. I mean, we need some way of, it's like two engineers looking at a bolt that they're about to put in a bridge and being like, one of them holds it and is like, yeah, I think it's good. And the other one's like, I don't know, man, it's a heavy bridge. You don't just go on a whim. Like, it just feels like it just seems like that's strong enough to hold this, You need something else, right? You need something else. So I'm going to show you, and let's see if I can convince you, all right? Now, this is going to get a little bit abstract. And draw a picture. So this is time, and this is distance. Both cars start at the same spot, and both cars end at the same spot. Do you agree? So here's the first car. No matter what it does, it's traveled a certain distance over time, and it needs to get to that point, correct? Let's call this A of t for car A, right? A of t is describing where car A is at every point in time. Now I'm going to draw the other car, which I will call B of t. And I just need to connect those two again, don't I? Doesn't matter how I do it. And I could come back here and do this 1,000 times, drawing them different ways. That's not important, all right? Call this B of t. You with me? Now, I'm going to define a new function, and I'm going to call it C of t. C of t is going to be A of t minus B of t. It's where A is at any point in time minus where B is at any point in time. Got it? Also, to help out here, I've already used T, and I've already used capital A and capital B. Let's call the beginning 0. Well, I don't want to call it 0. I want to be more abstract. Can I use little lowercase a and lowercase b here, and that'll be okay? You're not going to confuse those with capital A and capital B? Yes? So A is really 0, but let's just act like it's A. And B is whatever the time it took for them to finish the race. Yes? Okay. You ready? It's about to happen. Okay. Is C of t continuous? Well, is A continuous? Is B continuous? If you subtract two continuous functions, it's still continuous. When we were studying continuity, we were given that. The difference or sum of two continuous functions is continuous. So it is continuous, yes. Is C differentiable? Well, we're assuming that A didn't go from 30 miles an hour to negative 15 miles an hour in an instant, right? Like there was no abrupt changes in the car that would be physically impossible, right? It would be impossible to go from 40 miles an hour to 80 miles an hour like that, right? So assuming no weird sci-fi things are happening, then it's differentiable, right? By the mean value theorem, there must exist a point which I'll use little c in AB, right? Inside AB, somewhere inside, after they started, before they ended, such that what? The derivative of capital C at that point, little c, must be equal to what? C, or you could say what? C of B minus C of A over B minus A? Yes? But what's C of B? What's the difference between where they are at the end? 0. What's the difference of where they are at the beginning? 0. Right? C measures the distance between the cars, doesn't it? That's all it does. So the distance between the cars at the beginning is 0, and the distance at the end is 0, right? Do we still agree? And B minus A, who cares what that is? It's not 0 because B is the end point and A is before it. So isn't the right side 0? Yes? The mean value theorem guarantees us there's a point somewhere in AB where C prime is 0. But what's C prime? Go up here to C and take its derivative. The derivative of C is just the derivative of this, isn't it? How do you take the derivative of two functions that are being subtracted? Derivative of each one, right? What's the derivative of A? Well, A prime, right? A prime of C. This right here means A prime of C minus B prime of C must be what? 0. Now move this B prime to the other side. And what does this statement say? There's a point C somewhere inside the interval AB where the derivative of A is equal to the derivative of B. What's the derivative of a function if that function represents distance and time? Speed. It's velocity. This is saying the velocities are the same at some point in time. Guaranteed. Now, there's no arguing anymore. It is. That is the way it is. If two cars start and end a race at the same point, they start together, they end together, there exists, guaranteed, a point in time somewhere after the beginning, before the end, that they're both traveling the same speed at that same moment in time. Okay? I can't convince you any other way because we could argue about it. The math is the proof. Understand or not? I mean, we can sit there, but I still don't think. No, it's going to happen. See, what you would do now is, if you could just give me the functions, I could actually do it, couldn't I? I could figure out where it is. I would just define this new function. This is one of the first math problems that I ever saw when I was an undergraduate, where I actually realized that to solve a problem that seems really difficult required a clever idea to get through it. Like, where would you ever have come up with the idea of defining C to be the difference between the two, right? I mean, I did that. Why did I do that? And it was like the first eye-opening experience as a math person of, oh, wow, you mean to show things are true? You actually have to think way outside the box sometimes? Yes. And that's what makes mathematics very difficult, is because the proofs for things are not as simple as okay, quadratic equation, quadratic formula. You know, it's not like that. It's like if you want to break the window, it's not just throw the chair through the window. It's like, okay, you're going to do something crazy to get, you're going to have to get outside and come in the other way, and I don't know. You know what I'm saying? It's like to attack the problem, a lot of times in math, you have to come in through the back door. That's what we like to say that. You come in through the back door, you're finding other ways to address it that are just so unnatural. So you fail many more times in mathematics than you actually succeed when you get into the higher level stuff, because you're just swinging at it. You're just trying everything and pulling, trying to pull the rabbit out of the hat, and it's never a rabbit. And then finally you get it, and it's like that reward of getting it. So, all right. Wow, 210. Shall we do another example that's less theoretical and more like what you'd see on a test? Of course, that's what you want, right? Okay, fine. All right, let's do this one. Verify the mean value theorem. I think I'm going to just make one up and just see what happens. Function is f of x equals x to the fourth minus 3x to the third plus 6x squared plus 12 on the interval. I'll make it a nice interval, 0, 1. This is a fourth degree polynomial function, right? I would like to know where, if possible, inside the interval 0, 1, that it achieves its average value in there. So what do we got? What are we going to do for this? You want to do the derivative, get it out of the way? Okay. That's a nice derivative, right? You're like, just give me just 100, give me 1,000 of those on the final and I'm happy, right? I'm willing to trade any final that you're willing to give me for 1,000 of those problems right there, right? Give me an hour, I'll do them. I can do them in an hour. So is this correct? Is this correct? Okay, so now let's go through the process. I'm going to check first for continuity. Is f continuous? On 0, 1, absolutely. It's polynomial, of course it is. Is it differentiable? Yes, because the derivative is a polynomial. By the mean value theorem, we know this. The derivative at some point c must be equal to f of b minus f of a over b minus a. That's going to, I guess, be put into the memory banks or something for the test? And my college algebra class was all getting on me today because I am requiring them to know the properties of logs for their test. They want a cheat sheet, and I'm like, not willing to give them a cheat sheet, and they're all mad at me. 7 properties. You know, I'm talking about the properties of logs, like if you take a log and multiply inside, that it splits into 2 logs with addition. No, for log, not pre-cal. The natural log of 1 is 0. That time. So I'm going to expect that you can remember this for the test, the mean value theorem, just for the test. F prime of c is 4c cubed minus 9c squared plus 12c. That must equal, remember I said you're working left and right hand sides down, right? Together? Okay, what is f of b? Well, that's f of 1, isn't it? Not f prime of 1. F of 1. So what do you get when you plug 1 in here? See, 1, take away 3, add 6, add 12. So what do we got? 15? No. Yes? 16. So you get 16 minus f of a. A for us is what? 0. So just plug 0 into this. What do you get? 12? All over 1 minus 0, which is 4? Is that right? 4. Which is 4c cubed minus 9c squared plus 12c minus 4 equals 0. So I moved everything over to one side. Okay. Uh-oh. We're in trouble, aren't we? We don't have one in the last term. Almost. You could try grouping. It's not going to work. Synthetic is not going to work. I don't believe. I made up the problem, so the chances of it working are going to be pretty slim. What are we left with here? Third degree polynomial, right? Equation. Everything I heard is exactly what you would want to think. Grouping. If grouping fails, synthetic division. Highly doubt either one of them is going to work here. So what happens if synthetic doesn't work? What happens if grouping doesn't work? If it was quadratic, right? Right? My problem works. Mean value theorem guarantees the existence. There's a solution, I promise you. Now, can we get it? No. So there's a reason why I'm doing this. I don't, but that's not why I'm doing it. I'm just kidding. Now we understand the power of technology these days, right? We understand that we could just go to Wolfram Alpha, and we could just put this in, and it would solve it for us, wouldn't it? Let's do that, because that's what I'm leading you into, how the computer works, okay? How it's doing this. By giving you a problem that can't be solved by hand. So if I went to Wolfram Alpha, if I so desired, which is right here, if I wanted to solve that equation, what would I type in here? Probably solve, what is it? 4c cubed 9c squared plus 12c minus 4 equals 0. Let's just see what Wolfram Alpha does with this. If it's a fraction, or if it's an integer, then synthetic would have worked. Not looking like it was, though. Whoa. My goodness gracious. So it has a solution, approximate forms. So this will give us a decimal. Here we go. 0.45921 is the approximate solution. Now, how in the world is your calculator getting this answer? You can't, please don't tell me that a computer that only knows zeros and ones and on and off is better at math than us, right? I mean, how is it? Do they just sit there and go, oh, it's a cubic equation, no big deal? It's thinking about it. How does it do it? It relies on two things. It relies on the intermediate value theorem and the mean value theorem. And it exploits what those theorems give us. So let me explain what's happening. We're done with this problem. We can't solve it, okay? We have to just wave our hands at it and say we can't do it. On a test, I would never give you a third degree polynomial that can't be solved. It would be quadratic, or it would be third degree, but you could group it. Okay, something where it would be factorable by hand. So we're done here. But the solution is C equals, what was it? 0.45921. 0.45921. Does that answer live in this interval? Oh, yes, it does. It's guaranteed it was going to live in there, right? Okay, so how does your calculator do this? Let's get to that now. And this is going to be kind of a new idea, all right? So let's forget the mean value theorem problem, where this came from. Let's just say we started today and I walked in and said, okay, we want to solve this equation, all right? What can your calculator do better than you can do, and me? And what is it that it has? Let's not start talking bad about ourselves here. I mean, we don't be like, it can do everything better than us. No. I mean, computer is very fast, right? If I asked you to add up 100 numbers, you would have to sit there and add up 100 numbers, right? If I ask a computer to do it, it can do that in such a short period of time that it's insignificant to, it's like it didn't even do anything. So fast, right? So it has the advantage of speed of operations. So this is what your calculator is doing. It is taking this and it is ignoring this for a second and just looking at this as like a function. And it starts off by plugging in a number. So let's say it plugs in, I'm going to make this simple for us. Let's say it plugs in 0. What does it get when it plugs in 0? Okay, -4. So it would be very easy for the calculator to go 0 cubed, right, times 4, and then 0 squared, and then times that. Right? It could do all that. It's done. It gets -4, right? It stores that answer. Now it tries a different number, f of 1. Remember, it's trying to figure out when it gets 0 to come out, right? It's trying to get a 0 to come out. So it plugs in 1. What happens when you plug in 1 here? Three, right? And your calculator goes, aha. Well, it's not thinking, okay? It's a program. It says, when I plugged in the first number, I got a negative number. When I plugged in the second time, I got a positive number. Which means graphically, when it plugged in 0, it got a negative number. When it plugged in 1, it got a positive number. If this is a continuous function, right? If I have to connect those two dots, guess what it has to go through to get from the bottom dot to the top dot? It's got to go through and hit 0 somewhere in there, doesn't it? Your calculator already knows right now that the answer is somewhere between 0 and 1. It knows that because there was a change in signs. Do you see that? So what does your calculator do now? It cuts, 0, 1 is where it said, look, there was a change in sign, went from negative to positive, right? It says, let me cut that in half. Let me go to 1/2. Let me plug 1/2 in to the function. Now, again, that would take us a while, wouldn't it? But if you plugged in 1/2 here, you would get a positive number. So what does your calculator now know? It's between 0 and 1/2. So what does it do now? It cuts that interval in half, 1/4. And now what it does is it looks at 0 and 1/4 and tries to figure out if there's a change in sign. If there's no change in sign, which there wouldn't be here, it moves on to look between 1/4 and 1/2. And there would be a change in sign. So then it cuts that interval in half. And then it does it, and it looks for a sign change again. It cuts that interval in half. And it keeps on doing that. It's called the bisection method. And it keeps on, and what's happening is your interval is getting smaller and smaller and smaller. How small? As small as the preset tolerances on your calculator. Whatever the preset tolerance is within the program that's written to do that. Usually no more than 12 digits decimals. That means it's getting an interval when our answer here is 0.45921, right? What your calculator found is it's cut that interval so far, it's like this. It's reduced it down to an interval where maybe it's 0.459205, and over here it's 0.459215. All right? So now it knows it's between those two, right? Yes? And it's saying, hey, look, those numbers are so close together, because in the program it's telling it, like, at the end of every iteration, it's saying measure the distance between your two endpoints. Once that distance gets small enough, take the average of the two numbers, and that's the answer you're going to spit out. So it still doesn't know exactly the answer. It knows it's in here, and it's just giving you an estimate. The digits, how far out it goes, is dependent on the program. Does that make any sense? Okay? It's called the bisection method. It relies on the continuity of the function, that when you go from one point to the next, you have to pass through 0. Now, we are going to maybe, I don't know, it depends on time in this class. This was the first method ever really employed by a computer to solve equations, this bisection method. And even though it is fast, in terms of operation counts on a computer, it's very slow. It's primitive. And so there's better methods. And there's actually one in the book called Newton's method. There's an entire section on it. And what it does, I'll show you just a preview of it. It's really, really clever. Let's say that I have a function that does this. And I'm trying to figure out where it hits here, right? Yes? I pick a random point. Let's say I pick this one right here. I'm just going to call it x. I plug that into the function. Now, I take the derivative. The derivative creates a tangent line, doesn't it? Oh. That tangent line comes down. That's supposed to go through that point. And hits the x-axis here, doesn't it? That's pretty close to that red one, isn't it? So what I'm going to do is take wherever it hit the x-axis, I'm going to plug that back into the function. Then I'm going to take the slope of the tangent line again. And that's even closer, right? And then I'm going to go back up, and I'm going to do it again. And that gets you close to that answer very fast. That's called Newton's method. So, and then, you know, different algorithms are used for different computers, and there's a way better method than this now. In fact, it's gotten so good that Wolfram Alpha isn't even doing, isn't even doing that. It's doing symbolic manipulation. Like, it's actually giving you the exact answer. So it's not doing a bisection at all. Look at this is an exact answer. It's using a you know, there's a quadratic formula. There's a cubic formula also. It's using that formula here. I'm curious to know what would happen if I changed it to a 5th degree, because there is no known 5th degree formula. I wonder if it's going to give us an exact answer. My guess is it's going to be an approximation. A decimal answer. Yeah, see? So now I've pushed it to the limits of what it can do. So it's going to go to some method where it can give you a decimal approximation. Does that make sense? I'm somewhat off topic, but mean value theorem is just one of these weird sections in this class where it's like, what is this really all about? And it's verify the mean value theorem, left and right hand sides. That's what you'll be tested on. But there's a lot of like pretty abstract ideas in this section. One of the things we can do, and we'll wrap it up, is answer a question like this. Show that x cubed plus e to the x equals 0 has exactly one real solution. Show that this has exactly one real solution. What this is not asking you to do is to find the solution. There's a difference, right? Showing something, showing that a solution exists, versus finding out what the actual solution is, are two different things. So I need to somehow convince you that this has an answer. What's that? Okay, so look at this left side as a function. Then I'm really just looking to try and convince you that it has an x-intercept, right? So let's do what the computer would do, and let's try and figure out if we can make it positive and then negative somewhere. Can someone think of something I can plug in here that would give me a negative? Negative 1? What's f of negative 1? Negative 1 cubed is negative 1. E to the negative 1 is the same as 1 over e, isn't it? 1 over e is just a positive number, right? But how big is it? What's 1 over e? So it's smaller than 1. So this will be negative, won't it? This will be a negative number if I evaluate it. Okay? Then let's plug in something else. How about 0? Will 0 give me a positive number? 0 plus e to the 0. E to the 0 is 1. So that's a positive number. I'm done? What have I shown? It went from negative to positive, right? So it must pass through 0. Why? Must it pass through 0? It's a continuous. Is this a continuous function? So I'm going to summarize this. Since f is continuous and changes from negative to positive between negative 1 and 0, it must pass through y equals 0, right? The x-axis. Are we done? Can we pack it up and go? What have I not addressed? There's something I have not addressed. But I'm not looking for any answer. What does the question ask you to do? Show this has exactly one solution. Exactly one. I have not convinced anyone here. I think I've convinced you all that a solution exists. But have I convinced you that there couldn't be more than just that one? I haven't convinced you of that, right? I mean, what if you have a graph that does this and it passes through 0 several times? Right? I need to convince you now that this is the only one. That there is only one. So I would like for you to just look at these pictures. I'm going to draw two pictures here. This is an example of a function that passes through the x-axis 1, 2, 3 times. Here's an example of a function that only passes through the x-axis 1 time. Can anybody, just from those pictures, try and help everyone figure out what it is that I can look at that will determine that scenario to the right versus this scenario to the left from happening? We know it goes from, what, negative to positive? We know it goes from bottom up to here, right? Somewhere it goes from a negative to a positive. How can I convince you that it never comes back down negative? That right there would be enough, right? If I'm going to have another 0, though, what do I have to do? I have to come back down to this one, right? My derivative would at some point have to change signs, wouldn't it? it would have to go up, and then I'd have to make the turn to come back to the x-axis, wouldn't I? So my derivative would have to go from being positive back to being negative. Yes? That's critical. And it would work the other way around. If you went from positive to negative, went through the x-axis, if you were going to have another x-intercept, you would have to turn back up to get to it, wouldn't you? So somehow the derivative is connected to the behavior of this graph. Let's just take the derivative and see what we get. What's the derivative of this function? What is it, 3x squared plus e to the x? Somebody tell me something remarkable about that derivative. Think about what does, when a function goes up, what is its derivative? When a function goes up, the derivative is positive. When a function goes down, the derivative is negative. What is it about that derivative that you can tell me? Why? Okay, this number right here, I don't care what x you plug in, is positive. E to any number is positive, right? So you're always going to have a positive number here plus a positive number here. So regardless of x, your derivative is always positive. Yes? So that means the derivative is always positive. Therefore, f is always increasing. Going up, right? It's always going up. So it would be impossible to come back down to the x-axis. Impossible. So it is impossible for f to turn back to x-axis. So there's only one solution. I don't know what it is, but then I would employ the bisection method or Newton's method or go to Wolfram Alpha. Okay, let me give you some homework to look at here. Page 215. We have 1, 3, 9, 11. Short homework assignment here, 17. Have a great day.